Okay, hi everyone. Welcome to our sixth Cosmic Conversations talk for the year. And today we have Donovan Slabbert. He is a PhD student at the moment in quantum machine learning, and he did his undergrad and honors at Tux. He then moved on to BITS to do a master's in quantum optics, adjacent sort of things. And yeah, now he's here, and he's going to talk today about quantum machine learning for binary classification.
Yes, okay. Hello, everybody. Thank you for having me today. I would just like to say I am a first-year PhD student under the supervision of Prof. Francesco Petroni, who's also here today. And today I want to talk to you about using quantum machine learning on binary classification. We'll get into what those two terms are in just a moment. Okay, so just a quick table of contents, what we'll be talking about today. We have to define what quantum machine learning actually is. We have to actually know what binary classification is, the problem statement. Then we'll get into how quantum computing works, the basics of it, how to actually manipulate quantum bits, as we'll see later. And then we'll talk about the two methods that we'll be applying called quantum kernel method, specifically the quantum support vector machine variant, and also a variational quantum algorithm variant called a quantum neural network, a quantum convolutional neural network. And then we'll get into how we applied these methods to a specific problem, namely pulsar classification. All right, so to start, hello. We'll get into what quantum machine learning actually is. Let me just get my laser pointer here. All right, so you can think about quantum machine learning in four different flavors. It all depends on what kind of data generating device we have or what data processing device we have to actually process the data. So when we say generating, we mean, is the data classical or quantum of origin? When we say processing, we talk about the computer. Is it a classical or a quantum computer? We'll start with looking at the top left. The top left is standard classical machine learning. This is essentially data science or machine learning engineering. And this also includes using quantum-inspired algorithms to do classical analysis. That would imply that the other three blocks are what we would call quantum machine learning. And the top right corner, the green one, is classical data using quantum techniques, using quantum algorithms to do data science on classical data. The other two are different kind of flavors to quantum machine learning. One is classical machine learning algorithms applied to quantum data. And you can think about quantum optics, quantum information processing, and quantum computing as places where we apply quantum machine learning to optimize these various fields or to do some analysis. And the final one, quantum data with quantum approaches, would be simulating reactions in quantum biology and quantum chemistry. But for the purposes of this talk, we will be talking about quantum machine learning in the sense of doing data science with quantum algorithms. And now we know what quantum machine learning is, we need to understand what binary classification is. So let us take the problem as to define or predict whether a picture is a cat or a dog. So the input is an image, or let's say a number for that matter. It could be a series of numbers, but let's look at images for now. The goal of binary classification is simple. We want to find some trained machine learning model to take as input one of these pictures and to give us an output as a 1 or a 0, a dog or a cat. And this has to be as accurate as possible. So how do we do this? Well, some images or whatever sample will have features or input properties that we can label as numbers. Let's say the eyes or the tail or ears or whatever property a cat or a dog will have, we will have numbers representing these features, right? We will input these numbers in as a feature vector, a vector of these properties we will call X. We will put this into the machine learning model, and the goal is to reach a model where we output a label, a 0 or a 1, as accurately as possible. So this is the problem statement. Find a function f of parameters theta to be optimized so that we can take input domain X to output domain Y, features to labels. So there are three types of machine learning. This binary classification falls into one of them. The first type we have is one where we have no label. So let's say we had cats and dogs, but no labels. We didn't know if it was a cat or a dog. This is called unsupervised machine learning. And this, an example would be clustering. So let's say we have data of cats and dogs. We want to cluster them into dog breeds or cat breeds. Then this would be unsupervised machine learning. And we also have environmental learning with a penalty system for reinforcement learning. But specifically for our problem today, binary classification falls in the category of supervised machine learning. All right, next. How does training work? How do we find this model? Well, it's relatively simple. We have a data set with input features, X representing the properties of the object, and Y the labels. We want to split this into two into a test train split, where we now have a training set and a testing set. We simply take the training set, this one at the top, we take its input it into a model, train the model in some way. That is the target, to get the model. And then we want to use this model with the testing set to output some kind of predicted labels. And then after we do this, we do a cross-reference with the original labels in our testing set to evaluate how well our model did. After we did the training and the testing on the testing set, we then move on to real data that we have not seen before, and then we can actually implement the model from there. There are many ways of creating or training a model. We will talk about two of them today. And so essentially, supervised machine learning is we provide examples to the model, and then we predict on unseen data. Really simple concept. How do we evaluate the performance of such a model? We have a thing called a confusion matrix. There are 4 values here. They're called the true negatives, false positives, false negatives, and true positives. Think about a true negative as a cat being predicted as a cat. So you were correct in your prediction. And a true positive is a dog being predicted as a dog. False positives and false negatives, as the off-diagonal terms, are the incorrect predictions that you made. And depending on the problem, you would want to minimize both the false positive and the false negatives, but in some problems it might be better to minimize one or the other. And then from these values, we can calculate an accuracy value. The accuracy would be the amount of correct predictions over all possible predictions and overall. So the accuracy would be one metric. Then we could also focus specifically on positive and negative cases, where we essentially calculate the accuracy for only the positive and negative cases. We can also focus more specifically on how many of our positive predictions were in fact correct. Out of all positive predictions, only a certain fraction would be correct, and this proportion is really important to understand. And we can also average over the recall and specificity to get something called a balanced accuracy. This is very good for unbalanced testing sets, where, let's say, there are more cats in a testing set than there are dogs. You would need to make sure you kind of compensate for this imbalance in order to make sure that you don't bias your accuracy to a higher level because of your bias in one case or over the other. And we can also calculate an informedness and a geometric mean, also to kind of compensate for this imbalance sometimes. If you want to know more about these two metrics, I implore you to go read up on them. If you want to, I can also kind of explain later, but just for now, just know they are there to kind of compensate for imbalanced sets. And then the last metric that we can think about is training and prediction time. The longer a model takes to train or to predict, the more useless it really is. We kind of need the model to be as quick as possible. So now we know what the evaluation metrics are. We can now talk about how we move from classical bits to quantum bits, or what we call them qubits, in order to do quantum computing. So classical bits are a 1 or a 0, like in the matrix. You have an off and on switch, and we can represent numbers like the number 100 with this binary bit string. And physically, these things are transistors, or really anything that can be an on or an off signal in any computer or processing device. And so we want to move to a quantum version of these bits, which we will call qubits. We use quantum state vectors, 0 and 1, which we will together call the computational basis to do this computing. And these things have a really interesting property. It's called superposition. You've probably heard of this already, where we can actually interfere two bits together, two qubits together, or two vectors together to be in any state, to be both 0 and 1 at the same time. And then after we do some manipulation to this qubit and we measure, it will probabilistically collapse to either 0 or 1. We all know this. And then physically, there are 3 types. There are more, but 3 main types. There are superconducting qubits, trapped ion qubits, and optical qubits. And different companies try and create supercomputers, not supercomputers, quantum computers from these types of qubits. You can think of a qubit vector in the real plane as being a vector along the x or the y axis, and we can then represent a qubit state as a superposition of 2 basis states, 0 and 1, where alpha and beta are the amplitude values, and these alpha and beta amplitude values are related to the probability of measuring that state through the Born rule, which is inner products of the 0 and 1 basis state with the qubit state itself in an inner product. This is essentially projecting the state down onto either the x or the y axis in the computational basis. And here is the most general expression of a qubit that we can possibly think of. It has many properties. Some include amplitude, which is associated to the probability of measuring that state. In the Born rule, we have the phase, which is some distance, some relative phase difference that is related to the wave function of the qubit. And then, of course, the basis states, the 0 and the 1. These all can change, and they are all useful in encoding real information, the features or the properties of some sample as a quantum bit of information. All right, we can also visualize qubits on something called the Bloch sphere. So we have the most general qubit expression here. We can factorize out the global phase because since it's factorizable, it is not really useful in encoding information. So we'll just remove that entirely, and now we'll take this as our most general qubit expression. And you can see from the two amplitudes and the Born rule again that we have this relationship here, which is exactly the conservation probability statement, meaning that there are only two possibilities, a 0 and a 1, to be measured in a unit probability. The reason this is important will be clear now. And then just a quick note, you can also represent quantum states through density matrices, where this mathematical operation is the outer product, essentially almost like a convolution of two different state vectors together. This is only important for later when we talk about our projector matrix. We'll get to that soon. And so here's the Bloch sphere. It is a three-dimensional space. It's not the Hilbert space, which is the space of the bases, but here we just represent the state as a vector, where again, it's really important for this vector to stay on the surface of the sphere to have the unit probability. And this is where the link between conservation probability comes towards the Bloch sphere, for it to be a pure state. That's also something important to note. So we can visualize these states on the Bloch sphere. Then we need to know how to manipulate the qubits. So we have these operator matrices, we'll denote them O. We apply them to some qubit state, let's say 0, and we get out some new state. We can do this application, or we can model it by matrix multiplication. Really simple. Simply multiply a matrix with a vector. And then there are multiple types of these things. We'll only look at 4 examples here. We have XZH gates and RY gates, and you can think of these as bit flips, phase flips, superposition creating gates, or coordinate system altering gates, and rotation gates. And RY specifically rotates the qubit along the y-axis in the Bloch sphere. And all of these gates have one common property, that they are unitary, meaning that the actual matrix multiplied with its complex conjugate transpose is equal to the identity. And the reason this is important is, again, because of the conservation probability, keeping the vector on the surface of this Bloch sphere. So essentially multiplying one of these matrices with a vector on the Bloch sphere simply means moving it around on the surface. Okay, now that we know that 1 qubit gates exist, we can also extend this to multi-qubits. So we have a 2-qubit system. We have 2 qubits together, which we can write as a compound system by doing a thing called a tensor product, which we can write in 2 different ways. We can write either as a tensor product or a simple Foster wave. And then what happens is we essentially expand the state vector. We increase its dimension. So as we have more and more qubits together, as the system becomes more complicated, we have a state vector that becomes more complicated as well. And then we can do what we call 2-qubit gates, of which the C0 gate is the most common one that we use. This is a gate that does the following. It takes a control qubit. If that qubit is in state 1, it will bit flip the second qubit into a 1 state. As you can see, it takes this control and alters the state into a 1. This is a really important 2-qubit gate that we'll be using a lot. And then it is indicated as this, where this is the control and this is the target. And then again, operator matrices become more complicated as we increase dimension. All right, then finally we can get to the circuit representation of quantum algorithms. Here, wires indicate qubits. So in this case, we have 8 qubits. Right, so every wire is a qubit. So this would be a tensor product of 8 qubits to represent the entire state of the circuit. Each circuit has a depth and a width value associated to it, the width being the amount of qubits that we use, the depth being the amount of sequential gates that we apply throughout the circuit. Okay, at the end here at the right is an icon that indicates measurement. This is where we collapse the state vector to either a 0 or a 1, and when we observe the final outcome. Okay, so measurement means probabilistic state vector collapse, and we do many separate runs. We might do this thing 1,000 times, and we take as output of this algorithm the expectation value measured using the observable Z. This indicates the computational basis. So we take the expectation value as the output. And again, the Z observable specifies the computational basis. All right. Now, finally, we get to the general quantum machine learning algorithm, right? It has 4 distinct parts. A qubit initialization part where we simply initialize the qubits. We then prepare a state using an encoding mechanism where we essentially take the real data, the features, the properties of the cat and the dog, and we make it a quantum system, a quantum state. Then we manipulate the state in some way that we can control, and then we measure. Simple. So we can also change, like I said before, we can change the measurement basis by changing the observable matrix. So we can change from the Z gate to another gate to do a measurement in another basis. So this is the most general quantum machine learning algorithm possible. And now we will use this as a variational quantum algorithm where we train with a classical loop and classically optimized parameters like you would normally do in a machine learning algorithm. So here we have features, properties of a cat and a dog. We input this into the system. We encode using some gate. We essentially make the actual classical properties a quantum property. We make it a quantum state. We unitarily evolve it using some sequence of gates where we have parameters that we want to optimize. And then after an n amount of runs, we take as output the expectation value. And then we can do this multiple times where we optimize some sort of loss function. A loss is a similarity measure between output and expected output, or desired output, and we kind of try and minimize this. By doing this, we optimize the parameters to get the perfect parameters that when we input new data, the output will be exactly what we want. And then here's an example of how loss converges to a specific value, and we take as output to be this converged loss here. The parameters that cause this convergence will be the trained model. Okay, then we get to convolutional neural networks. We will combine this into the variational quantum algorithms together to form the method that we'll be using. So think about convolutional neural networks as a way of predicting whether a picture is a cat or a dog. So think about the image as our feature vector, and then think about a filter that we apply. Now we slide this filter across the image slowly, doing matrix multiplication with each little pixel, essentially scanning for what we call spatial properties of the image. So what we will get out of this after doing a convolution step is blocks of arrays called feature maps that essentially represent certain spatial properties of the picture. These could be the corners, where the corners are of the image. It could be where the edges are. It could be a color relationship. It could be an intensity relationship. It could be an ear to nose relationship, anything. It doesn't matter. We can't really tell because we're human, but the computer kind of understands the reason. And then from these feature maps, we can contract the dimension in some way. People call this max cut pooling, but just know that we kind of decrease the dimension of the arrays to make sure that when we computationally analyze this, that the computational costs are as low as possible. This is called a pooling step. And we can do this as many times as we like until we get to a decreased dimension as low as possible so we can do our problem. These are called hidden layers in the convolutional neural network, and one is called a convolutional layer, one's called a pooling layer. Once we've done this, we input this into something called a fully connected trainable layer neural network, where the nodes are called neurons or numbers, edges are weights. Every edge going into a node is an input. We sum these edges together in a weighted sum, and then this propagates forward, and we can essentially control the weights to determine what we actually do with the system. And then finally, we have one output layer, one node in the output layer, which will be a 1 or a 0 or a probability telling us which one of the cat or a dog it should be. So the main theme of convolutional neural networks is to analyze the spatial profile using filters and to reduce the dimension using max cut pooling. And so how does training work? We send in features from the start, the image. We do all of these convolutional pooling steps. We send it through the neural network where the weights are applied to it. Then we reach an answer. Then we send it backwards, using gradient descent to optimize the weights. The gradients of the weights are used to optimize the gradients. We send it back. We go back and forth doing a classical loop until we finally reach a point where we are happy with the loss convergence, and we take that as our trained model. And now we can reach the convolutional neural network point for the quantum version, where we now again have our encoding step. our SX, which takes the features into a quantum state, and we unitarily evolve it using this big block of code. And we can essentially represent all of these blocks of code as convolution and pooling steps by using a directed graph representation, similar to how the neural networks were indicated, where the initial step is 8 qubits initialized, and then we have a convolution step where each node represents a qubit, and the directed edges is essentially a unitary gate, one of those gates we talked about earlier, being applied over both of them. And what this gate is depends on your choice or your goals for the algorithm. You determine this gate. The same applies for the pooling step. Here you can see we have directed edges. Here they are just C0 gates. So we go for we take 6 here as the target, up to 3, and then we essentially reduce the dimension here. Now it's not an image now, it's only just qubits, but we are reducing the amount of qubits in our circuit over time to decrease the amount of time it takes to actually do the operations. All right, and you can do this however many times until we have a solitary qubit at the end. We measure that qubit and we take its expectation value as the output of our neural network. And then, okay, now we move on to the second method, a quantum kernel method. Okay, it changes a little bit. So the second block is no longer a parameterized quantum circuit anymore. Instead, it's the second encoding block. See, it's the same S, well, it's not the same S, but it's a similar S being applied, but now to feature vector X prime. Remember, the feature vectors are vectors that represent the properties of the image or candidate you want to analyze. So again, inputs, features are input on the left. And what this thing will now do is it will map the data, our real data, in features, in input space, into something called feature space. We'll get to that now. So there's a feature map that is applied to it. These methods require something called a similarity measure or distance measure that relates two features, X and X prime together, and then they use this later with linear methods to do the solving. We'll get to that. So what this method will do is it'll evaluate some sort of chosen distance measure in feature space, which is in our case the inner product because it's quantum mechanics, in feature space in the Hilbert space where we've now encoded the real data into, and then using this kernel value, this kernel function, these inner products, we can use linear methods to separate the data. And so there are no optimization loops or parameters to be optimized in this case. And here's an example of what a kernel matrix would look like, where each individual element is the inner product of two feature vectors. Okay, so this is kind of what a kernel method does. And now how do support vector machines work? What do we do after we have evaluated these kernel values? Let's take a two-dimensional example. So here we have input space. Let's say this is a cat and a dog. Cats and dogs are represented by X's and circles. And we have two input features. Let's say the tail length and the ear size, right? We can't really tell as humans where it is. So we apply our quantum kernel method, feature map to this, and then something like this might happen. The feature map splits the two data types away from each other, and then we simply just draw a line between the two and separate them. This is called maximal margin classifier, where the margin is the distance between the two black lines. This thing essentially endeavors to maximize this distance, and the red line is called the separating hyperplane. Why? Because sometimes the feature map is in a higher dimension, and so it's really simple. You just draw a line between the two. And then, of course, the dimension of the feature space after applying the feature map is usually higher than the dimension of the input space, but this does not always have to be the case. And in this example, the distance measure is distance, not inner product, but we'll be using inner product. Okay, and now we get to the method we employ, which is called quantum enhanced support vector machines. Again, you see the two encoding blocks, this time with rotation gates. So we essentially rotate a real value into the quantum state using rotation gates. And you can think about the state preparation phase as being both of these together, where we apply two rotation gates onto one qubit, and this is the output, where this difference here is important for later on the slide. And then also the combined effect can be modeled like this. And then after that we've done this, we measure, and measurement here is kind of different. We kind of design in a way to use a projector matrix of the shape of O hat. O hat is just the outer product of the initialized quantum state, the zero state with itself. So we need a projector matrix in the shape, and this projector matrix will be this specific bar here. we then find its overlap, its inner product with this state prepared state here, from here down here, and the output will be this, this probability value here. This will be our kernel that we use going forward. Now we will use a support vector machine with these kernel values as distance measure to fit the SVM and separate the two data types. The reason we do this, it's very specific. We want to do an inner product without performing a swap test. Why? Because a swap test would need another 8 qubits to be able to cross-reference every single qubit with each other and to actually calculate this. So this is a very technical reason, but if you want to know more, you can go look at this specific site here. Okay, all right, a quick note on our problem. The problem that we apply these two methods to is to predict a pulsar as being a pulsar as accurately as possible. And the data set that we use is called the HTRU2 data set, which has 18,000 instances with 8 features, meaning 8 inputs, so ears, tails, whatever of the dog. And then there's about 10% positive cases, meaning the pulses that we want to identify, and then the rest are all negative. So it's a 10%, 90% split roughly. Here we have the list of the input features, which are statistical derivatives of the integrated profile and the DM-SNR curve. These are two very important concepts in pulsar physics. I'm not sure what they mean, to be fair. But yes, if you actually know about this, then you know why they're important. And then just for completeness sake, I also include the correlation matrix, which shows what features are correlated with other features. And if you quickly look at this, you can see that here's some white here, but the rest are all correlated enough to kind of justify why we use all 8 features. This is for people who actually know machine learning a little bit more. All right, next, we start simulating these two methods, the quantum support vector machine and the quantum convolutional neural network, using simulators on a classical device, so no real quantum computers yet. We have 2 scalability statements for these two, where the time it takes to train the models depend on the amount of training samples in our training set. If you remember, we created a training set and a testing set. The amount of training samples determine how long it takes, and these are the 2 scalability statements, the number of epochs here, the number of iterations in the classical loop for the neural network part. And we can also get similar scalability statements for the prediction times, where this time here is the time it takes for one circuit execution to be applied. So we have this number multiplied over every time. All right, so we fixed the amount of testing samples to be 400 across both cases, and we train on 200 samples later on, but for now we'll vary the amount of training samples, and we fix the amount of epochs as 150. And out of this, we can find these 2 plots where we have a linear increase in training time and a quadratic increase in training time for the 2 different methods, green being the QSVM, purple being the QCNN. We see this intersection here, which means that roughly below 200 samples, the QSVM is faster, and roughly and above 200 samples, the QCNN is faster. For the prediction times, the reason the green line is so far above the purple line is simple, because if you go to this statement, this is kept constant, so it has to be a constant because this is also just a value, and this thing scales it linearly up. And the reason this one is lower is simply because of that linear gradient that takes it up. And this is another reason why you would rather prefer the QCNN, because its prediction time is so much faster. Also, another thing that's worth noting about the QSVM is it has to refer to both the training set and the testing set size in order to get an accurate reading, where this one only looks at the testing set. Okay, next thing is something called the confusion matrices. We had these before. This is the result of the prediction using the models on a 200 training sample training set and a 400 sample testing set. The bottom left is the thing we would call the false negatives. These are pulsars that were incorrectly predicted as being a non-pulsar. As a pulsar scientist, you would want to avoid this as much as possible, because you would, when you use this model on untrained data, you do not want to you don't want to predict a pulsar as a non-pulsar, because then you'll miss out on discovery, right? So you want to minimize it as much as possible. Then the other one, this one, the true negatives, meaning non-pulsars predicted as non-pulsars. This is already high because of the 90-10% biased towards negative cases. So both models become really good at kind of identifying them because it is so easy to kind of predict them both. Then I include another confusion matrix here, where on the right side, we have all the positive predictions. You would obviously want to avoid having as many, you want to minimize this block as well, just as you would want to minimize this one, but you want to minimize this one as well, but it's not really as important for you to minimize this as long as you get enough here and your positive predictions are fine, then you can actually go double check these manually. And as long as it's not as not the order of 300 and maybe that's like 4 or 5, then actually manually checking it doesn't take that long. All right, so we want to minimize this as much as possible, maximize this and this one, and kind of minimize this one as much as possible. All right, now do more samples helps, and now we'll increase the sample amount and see if the performance metrics actually increase. So what is the expected behavior if we have a plot of performance metric over sample amount? Well, we would expect some sort of increase, right? Well, this increase might not be exponential. It could be linear, we don't know, but I would say expected behavior would be it increases a lot at the start and then kind of slowly fizzles out with diminishing returns as it kind of plateaus out. This is called saturation or plateau. And you can kind of see this in the actual results where it slowly increases a little bit, very fluctuating, a lot of noise here because it's quantum mechanics, it's very probabilistic. It goes slowly up and then it kind of plateaus out. You can also kind of see the increase here of sample amount for the precision in the QSVM. Again, green is QSVM, purple is QCNN. These are all the different metrics we talked about earlier. I think the two most important to look at would be recall and precision. Why? Because these take into account how many positive cases that we predicted are in fact correct. The other two that focus on the negatives are slightly inflated. Why? Because it's so easy to actually predict negative cases. Of the two, I would say that this one is the more important one to look at of these two, because this actually takes into account how many false negatives we predicted. Again, pulsars that were incorrectly predicted as not being pulsars. All right, how does it compare to classical machine learning? This is the big question that everyone wants to ask. This is the reason we did this test. And from this table, it should be relatively clear that classical machine learning is better than quantum machine learning. I applied what you would call a off-the-shelf classical machine learning method to this problem, and these are the results. These are the curated versions of the quantum methods I employed, and you can clearly see that the quantum versions kind of keep track of the classical versions, but they are all sometimes, most of the times they're kind of lower. And the format of this table is average plus or minus standard error, just over 6 distinct runs, just for interest's sake. Specifically, let's look at this value here. This is the only value where the quantum case is higher than the classical case, the classical version. And this essentially means that for some reason, we don't know why, quantum neural network, quantum convolutional neural networks, the one I used, is really good at avoiding specifically false positives, meaning predicting non-pulsars as pulsars. Again, this is the one we don't really care too much about avoiding. We care more about avoiding the false negatives, but this is still a good thing to kind of look at. So for some reason, the QCNN is good at avoiding this. Can we then change the architecture of the quantum convolutional neural network to be biased towards the other case? Perhaps we can. So this is kind of still a good result. And then here, for some reason, this convolutional neural network, the classical version, this value is very low. The reason this is so low is simply because the classical convolutional neural network we employed was a off-the-shelf method. So if we actually had to improve its architecture, this value would probably most likely increase. So don't read too much into this negative value here. And then obviously the big one here would be the training and prediction times. Obviously, classical machine learning is much faster. So in order to use quantum machine learning, we'd have to do many runs to make sure the probabilistic nature of quantum mechanics is kind of accounted for. We need to fix the readout and measurement times to decrease this time as much as possible. And then perhaps when we have enough qubits and a fast enough runtime, these values would be equivalent, if not better, to this. But for now, in our current NISQ era, it's not the case yet. Okay, and also just remember that negative case focus metrics are slightly inflated, which is why this specific line are all so high. Okay. Now, finally, again, we look at the scalability statements we had earlier, and now we apply this to real devices. And so we actually measure these values, these circuit execution times, to be 3 seconds and 142 seconds across the two methods. We use the scalability statements, and now we simply plot the same plots as earlier, and you can clearly see the time it takes is much longer on a quantum computer for now. Hopefully these numbers will be drastically decreased once our measurement and readout times become faster in the quantum computers. But now the main difference in the plots is that for now this parabolic curve here for the QSVM is actually below the QCNN for the entire range of samples we tested for. Yes, there would be an intersection somewhere here if we had to extrapolate further, but this would mean that for real devices, the quantum support vector machine is faster. And the reason for that is because it's a shorter depth circuit. It was only 2 gates instead of the 15. And then a final note on noise. So another problem with quantum computers that we have to get rid of is called noise. There are people trying to mitigate and correct these things, but that's a talk for a different day. There are 5 main types of noise. The first one is environmental interaction. This is the study of open quantum systems where your quantum qubit state kind of gets entangled with its environment, and then this causes decoherence or loss of interference, or dissipation, which is a loss of energy. There's also thermal noise, where energy fluctuations in the system or energy level jumps can cause loss of information or relaxation. There's measurement errors, where when we measure, yes, quantum physics is probabilistic, so it's either a 0 or a 1 at some probability, but sometimes the measurement is actually incorrect anyway, which you can't really tell. But when you finally get the statistical distribution at the end, it would not be the distribution that you expected. So this is called measurement error. Another one is called crosstalk. This is when different qubits interact in a way we don't intend, and this causes bleeding of information across the 2 qubits. And a way you can kind of see this is here we have 15 quantum states or 30 quantum states, and then they kind of interfere at higher values of this value. If you want to know more about this plot, I can explain some more, but for now, that's where I'll leave it. And then the final one, which is the one I care about most, is gate-based error. There's a probability associated with each gate being applied to a qubit where an error can occur. And this would mean that for longer depth circuits, meaning more gates in sequence, you would have a larger error rate. And this is why you would keep your circuit as short as possible. And so this is the one that we care about. These gate-based errors come in many shapes: non-unitary evolution, where we don't preserve the probability anymore, and or incorrect manipulation. Think about, we want to have it as a 1 state, but for some reason it flips it to a 0. And this is exactly how we model this with bit flips. So we'll now model gate-based error as some probability with bit flips. The typical values of this probability of these orders, it seems relatively low, but when you have a really long circuit and you add up all these probabilities, then it can really become quite intense, and to the point where your results can be, I'll get to you now, okay? So again, more gates would mean an increased gate error, and if you look back at the width and the depth values, clearly the QCNN, which has a larger depth, would have more noise. And when we look at the balanced accuracy specific metric at an increasing amount of noise levels, you can see a decrease of the balanced uncertainty. At this point, it's completely random. Why? Because the bit flips were completely random. And the reason this starts so low is simply because the QCNN is so much longer than the QSVM at this point that even a probability as low as 0.01 is already a high enough noise for it to be this low. If we had a fourth data point at a probability of 0.001, perhaps this would be a comparable value. This is actually something I want to check. And so basically QCNNs are more vulnerable to bit flip noise. So the final question is, which method is better? Well, it depends, but binary classification, can they perform it? Yes. Are they better than the classical equivalents? Not yet. When we look at specific metrics, which one's better? It depends on the metric. Which one is better at avoiding false negatives? The QSVM for now. Which one is better at low samples, meaning better performance metric at low samples? The QSVM. And one is faster at low sample amounts, another is faster at higher sample amounts. The QCNNs are faster in general because of the prediction times. And which one is more noise robust? The QSVM. So probably the QSVM. If we're talking short term and perhaps long term if we fix the noise errors. But it depends on your problem and the design of the circuit. All right, and hopefully to be on the archive soon and hopefully published later is the paper we're currently writing. I'm working with both Prof and Matt also, which is also here. And also I just want to have a quick moment to thank SAQT for funding my studies. Without them, I wouldn't be able to be here. And with that, thank you. And I hope I actually didn't go too fast. Yeah, okay.
Thanks, Donovan. If there are any questions, please feel free to ask.
Sure, yeah. Okay, let's go back. You were at the noise one here, right?
I was just sort of worried I was reading that. Because I would reckon saying that means that for a 1 or 2 qubit gate, probably you can go up to as high as 1.1, 10% probability.
Sometimes, yeah. It really depends. Yeah. It depends on the device. And these specific values were taken straight off of IBM's website. Yeah. Sometimes it can be as high as that, but normally they are of the order of to the -3. Yeah. Yeah. Yeah, it can be quite high. This is why there are error mitigation techniques where you essentially multiply the final result with something, some factor to kind of fix this error somehow. You can kind of read up on that as well if you want to. Anything else? Sure.
Yeah. What did you mean by off the shelf?
Off the shelf, literally, I took a tutorial on the internet and I just applied that method to see how it does. You know, simple. Well, not a pre-trained model. I trained the model myself, but the architecture of the model was just taken off the internet somewhere. Yeah. And so if I had to go sit and actually think about how to make it work for the problem as best as possible, the performance metrics would really go up higher. But this is for the classical case, not the quantum case. The quantum cases are, apart from, I can obviously do more optimization, but they are as optimized as I can make them for now.
Is it unfair to compare your results with the probably highly effective and optimized classical methods?
We don't need to actually compare them with optimized classical methods because the classical methods as off the shelf are already better. So you would want, obviously as a machine learning engineer, you would want to be like, okay, let's take an off the shelf quantum method, just apply that and have it just work for you. And then maybe later you'll tweak it, right? But if we're comparing with classical methods and we're taking the worst possible performing classical method, and that's already better than the quantum case, well, then that's not really a good indication that quantum machine learning is as powerful as we want it to be, right? So we can definitely go and optimize the classical methods more, but it won't really tell us more because it will just be much better, even more better, really. So, yeah.
Would you expect quantum models to perform better than conventional models on QQ case? This is the CQ case.
So
for their performance, would you expect them to perform better on QQ case?
So specifically, if we look at quantum chemistry, where we model the active space of some molecule, this is the reactant part of it. This is really hard to simulate classically. There are methods called Hartree-Fock, and there are different kind of ways to do this. But yes, possibly this is the most promising place to perform quantum computing in general. For machine learning specifically, where we might predict something, perhaps that'll be the same, yes. Yes.
You might have explained it when you missed it, but you had a column called batch.
Yes. Yes. Okay. So I don't want to go too much into this, but so there's two types of QCNNs that we did. One, we trained every iteration on the entire training set. And in the batch case, we only train in iterations a certain subset of the training set. And so because of how we batch, this one will be much faster in training, right? Because this one trains only over 10 samples per iteration, where this one trains over 200 samples per iteration.
And it looks like
and they are kind of equal, exactly. So this is why the batch QCNN is considered faster, much faster than the QSPR. And if we go back all the way, let me just get out of the animation one, go all the way back to the to here. This is also why there's a purple line and the blue line here. The purple line being the one that trained over the entire training set every time, hence why it's so smooth, and the one that fluctuates because we train over batch. Okay. Yes.
Just a quick question. I know that like classical methods are not yet quantum computing methods are not yet on classical methods.
Yes.
But like in general, like why would you expect quantum methods to be better than classical? And
Why would you expect quantum methods to be better than classical methods?
especially for like quantum machine learning? And if that is the case, then, like where does the speed up come from? Does it come from the encoding?
Yes. So the readout and measurement times for now are slower on quantum computers, right? But there's this thing called there's twofold really. Theoretically, quantum support vector machines are guaranteed to be at least as good as classical equivalents, or even slightly better. I can't prove this, but there are papers that have proven this, specifically for the kernel method side of things. As for why would you do quantum machine learning in general, or quantum computing in general, a good example would be to think about the Grover algorithm, where we have a provable speed up as well. Again, it'll be slower than classical methods because the readout times are so slow for now. But it can be proved that less operations are needed to do what a classical computer can equivalently do. And this almost like a parallelization does come into play in quantum machine learning as well. But yeah, that is a very difficult question to answer. Yeah. Yeah.
What are like some common approaches to initialization or to coding feature space?
Yes. So the main three are, as I said earlier, let me just get to there. The main three are amplitude, phase, and basis encoding. The one I did is kind of like a phase encoding. We essentially rotate our feature into that block sphere, right? That is angle encoding. But amplitude encoding essentially means that we take this alpha value or beta value, and that becomes our information. And obviously, we'd want this to be a value between two values between 0 and 1, or together they are, they conserve the one unitary. And also the basis state, we can actually use the basis state itself to represent something. And a good example of this is in quantum optics, or quantum information processing using optics, where you can use something called OAM state, orbital angular momentum. And these things actually represent a specific bit of information, and the probability of measuring it then kind of also relates to that. So, does that make sense?
The choice of the basis states that we have, so the choice of like the binary atom.
Yes.
Obviously leading on from computer.
Yeah.
That seems like an actual choice leading on from one computing.
Yes.
But do you sort of think we'll abandon that as we go?
I think we might have to, because superconducting qubits from IBM have their limitations. Because they're superconducting, they need to be at a very cold temperature. But if you look at optical quantum computers, one where they use, like I said, compound OAM high dimensional states, you can actually do a lot more information processing using, they call it qubits, where D means n dimensional. So perhaps we might have to move away. There's another field called what's it called? Quantum. What's the word called? I can't remember. Whatever. There's a thing called Q modes as well, where you essentially use continuous variables to encode. It's quantum wave functions, but it's a continuous variable. It's a really odd thing, and they have these quantum states called cluster states. And it's not really usable physically yet, and there's no programming language for it yet. But essentially, we can have millions of these Q modes to encode information. This might be a way forward for quantum computing. Yeah. Cool. We're done.
Great. Thanks, guys.